Coordination compounds often have isomers. And let's refresh our memory on what isomers are. These are compounds that have the same formula but different structures. And we can divide those isomers into two broad categories. One is structural isomers. Here the atoms are connected differently. So, you might have the carbon attached, but the oxygen attached to the metal ion, or the nitrogen attached to the metal ion. It's different in that way. Or you can have stereoisomers, where the connectivities are the same, but the spatial arrangements are different. And then there are subcategories. Coordination isomers, where the ligand and the counterion exchange places, or linkage isomers, where the ligand coordinates to the metal in different ways. And for stereoisomers, we can have geometric isomers and optical isomers. So we will talk about these. So a coordination isomer occurs when the ligand exchanges places with the uncoordinated counterion. So look what's happening here. In this compound, bromide is one of the ligands, right? It's inside the brackets, and the counterion for this is the chloride ion. In the other isomer, the chloride ion is a ligand, and the bromide is the counterion. They've swapped places. You see how that's different? It's the same but different. These are going to have the same molar mass, the same empirical chemical formula, but they are actually different compounds. In a linkage isomer, the ligands are attached in different ways. Not all ligands can do this, but nitrite ions can form coordinate covalent bonds through either the nitrogen atom or one of the oxygen atoms. And so it's going to have a different name depending on how it's attached. If it's attached at the nitrogen is called nitro, and if it's attached at one of the oxygens, it's called nitrito. So here we have pentamine nitro cobalt 3. So nitro means that this NO2 group, this guy right here, is attached at the nitrogen. The lone pair on this nitrogen is forming a covalent bond, a coordinate covalent bond with the cobalt ion. And this is kind of a yellow-orange in color. If that nitro group is attached at the oxygen instead, then it's called nitrito, and the color is different. And we can look here at the ball and stick model here. We've got the nitrogen attached to the cobalt, and over here we have an oxygen attached to the cobalt. It's a very small difference, right? But they are different. So these are some other ligands that can do this. The cyanide ion, cyano if it attaches at the carbon, isocyano if it attaches at the nitrogen. We can do the thiocyanate ion, can do that as well. And that's cyanide, this is cyanate. Yeah, cyanate and thiocyanate and cyanide. Not confusing at all. Any questions? Aren't you glad you didn't have to memorize this? Phew. So geometric isomers are in the other category. These are stereoisomers. Geometric isomers happen when the ligands have a different spatial arrangement. So all the connections are the same, but they have a different spatial arrangement. So we can look at the two isomers of this. That would be, let's see, diamine dichloroplatinium 2, I believe. So here we've got our platinum ion. This is going to exist as a square planar complex ion. And so we have basically the four corners of a square here. If we have the chlorides next to each other and the ammonias next to each other, this is called a cis isomer. Cis means same side, and trans means opposite side. So here we have the ammonia groups on opposite sides of each other, and the chloride groups also opposite to each other. Any questions? So that was a square planar. It can also happen in octahedral complexes. So here we've got cobalt with 4 ammonias and 2 chlorides. So here we can have these 2 chlorides next to each other along the axial plane, or they can be across from each other. So this would be trans because these are across from each other, and this is cis because they're on the same side, they're next to each other. You can't have cis-trans isomers in a tetrahedral complex because each corner is already adjacent to all of the other corners. And so there's no cis and trans for tetrahedral structures. This is another type of isomer that happens with an octahedral structure. Let me go back here real quick. This happened with the general formula where you have a metal ion and you have 4 of one kind of ligand and 2 of another kind. This kind can happen when you have 3 of one kind and 3 of the other. So we can have the chlorides here so that they are at the corners of one of the faces. So this is a facial isomer, the face isomer, and this is the mer isomer, where these are along the meridian of the molecule. And you can see if you look at the other ligand, they're doing the same things. This one is also a meridian, and this is forming one of the faces. So face-mer isomers. These things require good spatial visualization or making little models. If you don't have a model kit, that's okay. Toothpicks and marshmallows. Toothpicks and gumdrops. Get creative. Okay, draw the structures and label the type of all the isomers of each complex ion. So here we have chromium, and we've got 3 water molecules and 3 chlorine molecules, or chlorine ions. So what kind of isomerization is possible here? The facial meridian type, right? So let's see if we can illustrate that. Okay, so I'm going to draw circles for each of these things. So water's just going to be a single circle because otherwise it's too messy. So this is my chromium in the middle, and this is octahedral, and so I've got these guys. And then I'm going to make water, I'll make water blue. So if I put water here and here and here, and I'll make the chlorine green. What do these 3 chlorines form? They form a triangle, one of the faces, right? And this also forms a face. The other option is to have them in a straight line. So we could have them arranged like this. So here, this is at the top and the bottom and the side, so it's going along the meridian, right? And in the vertical direction, and this is going along a meridian in the horizontal direction. So this is the mer isomer, and this is the face isomer. Is there anything else that we can do with that? Are any of these ligands that could attach in a different way?
Can you just swap the positions of the blue and the green so that way the blue is like top and bottom? Or does that matter?
Well, if you mean if I swap these two
Oh, I was talking
on this one?
Yeah.
So if I swap like these guys?
Yeah. I mean all of the positions, but yeah. Oh yeah, I guess one.
So if you switch any two colors, it becomes the other one. Yeah. Okay, so this one on the bottom here has oxalate. Let's just go back and look at the oxalate. So this is oxalate here. In the name, it becomes oxalato. And no. So here's the structure of it. Is this going to attach at just one oxygen, or is this possibly a bidentate ligand? This can be a bidentate ligand. You can have both of these oxygen attached to the central atom. Okay, so we've got two ammonias, two chlorides, and the oxalate is going to occupy two places in the octahedron. So we'll have chlorine be green again. And ammonia can be orange. I don't know why. And then we'll make the oxalate purple again, for no particular reason. So now the question is, can we attach those and make different isomers? It's hard to think about, isn't it?
Can't you switch an orange?
Yeah, I accidentally stopped recording somewhere. So here we have one isomer, and by switching a orange and a green, now we can have the orange ones directly across from each other. This is the trans isomer. This is the cis isomer. Everybody is next to their friends. So I made a trans isomer. So here's the cis one. I made a trans isomer. Is this the same as the one I drew? No, what's different? Now the oranges are next to each other and the greens are across from each other. So apparently there's a third one. So again, we'll leave oxalate down here. And now we'll put the orange ones next to each other and the green ones across from each other. So that would be a different isomer, right? This would be trans with the chlorines. I forget which color was which. I think green was chlorine. Here, the greens are across, is trans for the chlorine, and the other one is trans for the ammonia. And that's what that one looks like. So here, the ammonias are across from each other, and here the chlorines are across from each other. So they're different, right? So this one appears to have 3 isotopes. I'm sorry, isomers. Any questions?
Is there another one for the cis one if you swap like the?
That's a great question. Is there another one for the cis? I don't think so. I think it'll just be rotated.
The opposite though. What's if you, from the fraction of the purple, if you switch the 2 poles, would it be different?
There's just nothing like an actual model to help with this.
And the workout that comes with it.
It's not usually this hard. Okay, so these are the same, right? And now they look different, right?
Yeah.
So here, the orange ones are next to each other in the horizontal, and the green are next to each other in the vertical. And here, the orange is vertical, and the green's horizontal.
But what if you switch like the 2 ends, like the green and the?
These two?
Yeah.
You can imagine what it's like when you do a lab where you got 30 students using these models and that little sound.
I don't think they went up the Yeah.
No, you're right.
It's exactly opposite, right? Yeah.
You're right. Those are different. So then we have to draw another one in here. So, you can do things the hard way or the easy way. And what was I doing? So it's best to keep it as similar as possible in your drawing and try to only change one thing at a time. So here, from here to here, I switched those like that. And so let's try switching these two. I think that's what we need to do. So that's the one on the left. And this is the one on the right. And they are different. Good call. So So there's two different cis isomers and two different trans isomers. Would any of these be facial or meridian isomers? No, I don't think there's really any way you can think about it that way. We can also have optical isomers. So optical isomers are non-superimposable mirror images of each other. And when we have molecules like this, they're called chiral. The isomers are called enantiomers, and they exhibit optical activity, which means if you shine polarized light through a solution of this stuff, it will cause the light to turn. It's crazy. So what we did here, kind of inadvertently, is we have two optical isomers here. So this one looking in the mirror would look like that one, right? This is like your hands. Your hands are optical isomers essentially of each other, right? They match, for most people. They match, right? But you can't superimpose them, right? That's why a glove really only fits well on one hand, right? Because the pinky and the thumb are different. And so they're not the same, and yet they're the same. That's what chiral molecules are. So here, we're looking at the mirror image. So we've got this guy up here, that guy is just like looking in the mirror. And we take this down here and we try to rotate it and make it match up with that, and we can't. So this is an octahedral complex where we've got optical isomers. You can have optical isomers in tetrahedral complexes, but all four ligands have to be different. So determine whether the face or mer isomers of, let's see, what's that called? Triaqua trichlorochromium 4? No, chromium, yeah, chromium 4. Well, let's draw one of them. Oops, that didn't come up very well. So we've got 3 waters and 3 chlorines. I'll do blue for the water. And green for the chlorine. What kind of an isomer is that? It's the facial or face, right? And so now, actually, leave a little room here. I will draw the mer, where we've got I'm going like this. What's the mer isomer? And this is asking, determine whether either of these is optically active. So to do that, we would draw the mirror image of this and then see if we can rotate it and see if it's actually the same thing. So I'm going to draw the mirror image of the mer. So many octahedra. So the mirror is right there. Well, Now, let's play with our little models here. Sure. All over the place. Okay, I made the face one. Wait a minute, I can't make that line up. It's good when you can drop things and catch them before they hit the ground. Okay. Because they're new. Okay, so here we have mirror images. They're facing each other, right? So now let's see if I can make them be the same. And yes, I can. You see, so the greens are lining up, and the blues are lining up with each other. So those are the same molecule. So that's not optically active. That's just the same thing. Okay, here, make those into the other things. That's what happens when you sit in the front row. So, and if you haven't looked at it yet, the take-home exam for this chapter has you do stuff like this. Okay. So let's line these up. I'm doing it facing myself because it's confusing enough. Okay, mirror images, right? And they line up. No, they don't. They're not lining up, are they? It's just because I'm doing it badly. There they go. It's like, wait a minute, this isn't supposed to happen. So those are actually the same as well. So neither is optically active. So optically active or chiral is when you can draw the mirror image and you can't, by just rotating it, make it superimposable on the other one.